Good afternoon, everybody. Let's get started. Welcome to Introducing Data Intelligence to Delta Lake with DatabricksIQ. Quick introductions first. My name is Sirui. I'm a product manager at Databricks, working in the storage space, working on Delta, based in Seattle. It's good to see you all. This is my colleague, Terry.
Hi, everyone. It's really great to see you. My name is Terry. I'm a software engineer at Databricks working on the storage layer and Delta Lake. So if you have any topics to discuss, come find me after the talk.
Terry is incredibly modest. He is the genius behind liquid clustering, if you've heard of that, as well as a number of other technologies. So it's a big get for us. Yeah?
Oh, thank you.
Yeah. So you're going to hear from the inventor of liquid clustering how it works in just a minute. But before that, what are we here to solve? So this is a more deep dive talk. So we're gonna look at some code. Now, before the data intelligence platform, what we're gonna do is we're gonna start by writing a simplified view of the code that might be required to make Delta Lake run quickly and efficiently and cost effectively. So the first thing you gotta do, of course, is create a table. But then from there, historically, you've had to reason about a number of things. The first one being, what's a good target file size? You have to worry about file sizes. And this is true not only on Delta Lake, but with any open lakehouse format, because this is just the first principles of accessing data from cloud storage. So what do you have to do? Well, in Delta Lake and in most other open formats, you can tell us, well, what's a good target file size to aim for? And then after that, you could tell the system to do writes in certain ways to try and get the file sizes closer to that optimal. So there were two capabilities we've historically had: optimized writes and auto compaction, where at write time, like when we're doing the write, you can do certain things to make file sizes closer to the target that you set before. So that was one chunk of things that you had to worry about. The second thing that you had to worry about after that was the data layout strategy. So you'll notice that even when you created the table, you had to select what columns to partition by. That's obviously an industry standard, really important for performance, but pretty complicated because there's certain rules for what you can and cannot partition by, or at least best practices. And then for columns that you don't want to partition by because maybe they're too high cardinality, what you could also do is something called z-order, which is a way of clustering data to similarly get good performance. But you have to worry about that, right? Which columns to cluster, which columns to partition by, how do you choose one or the other? And if things change historically, this is a bit of a mess. And then the third thing you had to worry about, also true across lakehouse platforms, is constant maintenance. So one example of this is gathering statistics. There are all of these statistics that you can gather to improve data skipping, to help the query optimizer decide, for example, what kind of joins to perform. But these required, historically, a certain level of manual elbow grease to make sure that you were running these analyze commands and configuring them properly. And then on top of that, don't forget to run optimize and vacuum. These are really common commands which make sure your file sizes are correct, which does basically garbage collection to get rid of files that you don't need anymore. So that's a lot. That's a lot. And even if you define all of this once, I mean, you've just done this for a single table, but you still have more questions, right? You have questions like, well, is your current system, is how you've written the code actually doing a good job? Or if you were to tune it, could you do better? And even if you realize that you were doing a great job on day one, maybe things change after 3 months or 6 months. Data patterns change, query patterns change. So should you revisit it? How often should you revisit it, right? And also, how does this work in a decentralized large organization, right? If you have a central platform team, does the platform team do this? Do they publish best practices for someone else to go do this and hope that their end users actually do this? It's a lot, right? So, we did a bunch of user research on this, and we actually have some footage from an enterprise as they try to figure all this out. See if you can pull that up. Good footage. Basically, it's a giant game of whack-a-mole, right? The moles keep multiplying. The data is going to multiply. What you don't want to do is play this game forever, especially as you try and democratize data in your organization. And so, this is where DatabricksIQ, the data intelligence platform, we believe, comes to the rescue. So what we're going to show you throughout this talk is that over the past few years, we've been able to use the data intelligence platform and the data intelligence engine to steadily automate away increasing amounts of pain and to help really simplify the code that we started with, right? So then the way this is going to work, we're going to return to this diagram over and over again, is that the data intelligence engine is a continuous feedback loop that gets smarter as you use it. So it starts with telemetry that we gather. The engine understands your workloads. What tables do you have, the query patterns against those tables, and how your data is being used. And from there, it's fed into an AI model which determines the best optimizations to run. So what optimizations and configurations are best for your particular workload. And then after that, we don't stop there. The engine actually performs the required tuning and optimizations on your behalf so that you don't have to run these recurring jobs and things like that. Okay, so for the rest of this talk, let's walk through this code again, but let's see how the data intelligence platform is able to actually dramatically simplify this block of code down to, well, we'll see where we end up. So, okay, the first domino to fall for us was file sizes. That's this highlighted, yellow highlighted area here. So what exactly is the problem? Let's motivate the problem first. So as you all know, with Delta Lake or Iceberg or Hudi, all of these tables, what they really are is files in cloud storage, right? Files in S3 or ADLS or GCS. And all of your Lakehouse tables are made up of typically many data files. As you write to these tables, you get more and more files. And so with file sizes, if you have file sizes that are too small, what'll happen is you'll have a single table and it's made up of like millions or billions of files, and it's really expensive to go and grab all of those files from cloud storage. But separately, you also don't want a table where the file sizes are too large, because then it's difficult to make changes on those files or to do effective data skipping, because you can't skip a giant block like that. And so either extreme can cripple performance. And so the question is, how do you determine the optimal file size for the workload? And then on top of that, how do you make sure that even if you knew the optimal file size, that your file sizes are that in practice? And so what we did with the data intelligence engine, this is a great problem for AI to tackle. It's really great at tackling these kind of Goldilocks problems. And so we built an AI model which determines the best file sizes for a given table. And it weighs factors like the size of the table and the read-write patterns. This is trained on our fleet-wide data. And so it looks at your particular workloads. What tables do you have? How they're queried. It applies this model against your data. And it says, oh, what should be the optimal file sizes for your given tables? And then on top of that, we improved how we wrote using our clusters and our SQL warehouses. So we talked about before, there were these knobs you had before around optimized writes and auto-compaction. We were able to improve those enough that they didn't need to be knobs anymore, that they could just be always enabled. And so here in this first example, it's basic, but it'll get more complicated. In this basic example, we're determining the optimal file sizes for you, and then we're making the tweaks in your clusters and warehouses to get your file sizes closer to that optimal. And so we actually rolled this out more than a year ago, I think, at this point. But since we rolled it out, we saw a 30x increase in average file size. By the way, that's because what we saw in practice was typically file sizes were far, far too small. And because of this, what we saw, our benchmarking shows that as file sizes approach the optimal, you should expect more than a 2x query performance, because you don't have to go and grab all of those files. And so we're really excited about that. It's just the first step in our journey, but already you can see we're making pretty significant impact on query performance. Faster queries means faster time to insight and less money spent on compute. So that's the first leg of our journey. So thanks to AI-optimized file sizes, you no longer have to set these, tell us what your optimal file size is. You no longer have to set these knobs around optimized writes or auto-compaction. And so we wave our AI wand over here, and those lines of code go away. All right, so what's next? So the second problem we talked about was data layouts, right? So before, you had to set partitioning. You had to set z-order by, choose wrong, things slow to a crawl. If you choose right, you have to worry about what happens when your data patterns change. And so what can we do about that? Hand it over to Terry.
Thanks, Sirui. I'm so excited to talk about some of the new features that make Delta Lake fast and easy to use. Let me start with liquid clustering, which we announced as a GA feature a few weeks ago. But before I get into details, let me give you a background on why we worked on liquid clustering. As you may know, there are already existing techniques for optimizing the data layout, such as partitioning and z-ordering. They are good for performance, but tuning them to get the optimal performance is not straightforward. For example, you now mix partitioning and Z-ordering. So you have to make decisions on which columns go to partitioning and which columns go to Z-order. Also, we have to be careful about the cardinality of a column when choosing partition columns, because choosing a high cardinality column will not scale due to the small file problem that Sirui just went over. Lastly, if query patterns change and you want to change partitioning columns, you have to rewrite the whole table, which is not ideal. So let's go through one example where that shows some of the challenges with partitioning. Let's assume that we have a table that we decided to partition by date and customer ID based on our query pattern. And assume that we are ingesting data hourly. These are the data ingested in the first day. As you can see, we already have some small files ingested. More data ingested the next day, and more data ingested today. Now that we accumulated many small files, this could slow down the read performance. So what do? We run optimize to compact these small files. Optimize tries to compact small files, but it compacts only within partition boundaries to respect partitioning, as shown in the dotted green boxes. As a result, you have some partitions with good file sizes, meaning close to the target file size, but there are still many partitions with small files, which can degrade the read performance. One way to fix this is to partition by week instead of day to make file sizes bigger, but this requires rewriting the whole table, which is not an ideal solution. So to recap, I showed one example where partitioning cannot solve the small file problem, and you cannot change the partition columns for your needs without recreating the table. To solve the problem I described so far, we introduced liquid clustering. It is fast. In fact, write performance could be faster than partition and Z-order table. I'll share some results in a bit. And it has a similar read performance out of box, even compared to well-tuned partition and Z-order tables. Liquid clustering is incremental, meaning it clusters only data that needs to be clustered, which leads to low write amplification and fast clustering time. It's self-tuning and skew resistant, so you don't have to worry about the cardinality of a column when you choose a clustering column, which was not the case when you pick a partitioning column. Last but not least, it's flexible. You can change the clustering columns at any time based on your needs without rewriting the table. Let's see how Liquid works at high level. This is the same data set that was ingested to a partition table a few slides earlier. Now, when you cluster this table, liquid clustering intelligently figures out which files to be clustered together, which is shown in the green boxes. As you can see, there is no restriction on the value boundaries anymore. As a result, you get a good clustering quality as well as good file sizes. And this shows that liquid clustering can solve the small file problem by handling cardinality and data skewness automatically for you. Now, let me show you a quick example of incremental clustering. In this example, let's assume we ingested few new files, which are represented as dark blue boxes. And let's cluster this table. First, the files in the red box are not touched at all because they are already well clustered. As you recall, these are the files generated after you cluster table in a previous slide. How about this file in this red box? It's not clustered because the file is already close to the target file size, and liquid clustering figures out that clustering this file would not improve the clustering quality because it already contains similar ranges with other files in the same gray region. How about these files in the red box? These small files will be clustered to optimize for file sizes. So as a summary, liquid clustering intelligently selects files for clustering and cluster data only if clustering quality or file sizes can be improved. And this can reduce write amplification quite significantly, and in return, it improves the overall clustering time as well. Now let's talk about clustering on write. This is a feature where clustering happens on the fly during ingestion. In this example, let's assume that we have a large ingestion. In other words, we have enough data being ingested for clustering. And as you can see, liquid clustering clusters data during ingestion such that the newly clustered data respects the existing cluster data layout. So what are the benefits of clustering on write? First, it reduces the write amplification for clustering. Normally, you would ingest data and run clustering, doubling the bytes written. But clustering on write will get rid of this write amplification altogether. Also, since the data being ingested is clustered, you get a good data skipping right after ingestion without clustering the table again. So let's talk about conflict resolution. If we go back to our code, one use case for partitioning is to resolve write conflicts when there are multiple concurrent writes. Let me walk through one example. We have a table partitioned by date. Let's assume that we have one merge command that updates files for these 3 partitions in the green box. Now let's imagine we have another merge command that updates the files for the partition in the red box, which doesn't overlap with the partitions in the green box. In this case, there is no conflict, and concurrent updates succeed. But now let's assume that instead of the second merge command, But now let's assume that instead, the second merge command touches the files in the same partition as the first merge command. In this case, there will be a transaction conflict, and the second merge command will fail, assuming the first merge command is the winning transaction. And the user has to retry the merge command number 2 and hope for the best that there will be no other transactions touching the same partition. As you can see, handling conflicts in partition table can work, but requires careful orchestrations among business and maintenance transactions. Now let's see what happens to liquid tables. Here we have 2 merge commands that run at the same time. Let's throw in more commands such as optimize, update, or delete commands that run concurrently. And all the transactions can succeed. Why? Liquid table enables row-level concurrency by default, and it can handle conflicts as long as different rows are updated. So the resolution is now at the row level and not at the partition level, and it's more fine-grained. So with liquid tables, you don't have to worry about orchestrating business and maintenance transactions, making it really easy to use. So far, I have talked about incremental clustering, clustering on write, and row-level concurrency. And it's really easy to achieve all these benefits. You just use cluster by syntax when you create a table. And if you want to change the clustering columns, you can simply use alter table cluster by and specify new columns. In addition, you can use this same alter table syntax to migrate any existing unpartitioned tables to liquid tables in place, meaning without rewriting it. How about the performance? We measure the performance of writes, which include both ingestion and clustering time, using 1 terabyte industry standard benchmark dataset. In this setup, we also ran clustering frequently to keep clustering quality always high. And liquid clustering was 7 times faster than partition and zero table, thanks to incremental clustering and clustering on write, which I just described. We also have a result for read performance. This result is from a large manufacturing company, and they saw up to 12 times faster read performance after migrating partition tables to liquid tables. How does the adoption look like? We are overwhelmed by the customer adoption. Liquid clustering has been one of the fastest adopted Delta features. We have more than 1,200 active weekly users. This number is from the last week, and this number has been growing every week since public preview. We have a table bigger than 600 terabytes used by customer in their production workload, and we have many tables in the 100 terabytes range. And it shows that liquid clustering can scale. Also, there have been more than 100 petabytes written and 20 exabytes read from liquid tables since the public preview. Let me take a quick pause And can you guess how many bytes liquid tables help to prune in data skipping? That's 1.1 zettabytes. In case you are not familiar with zettabytes, 1 zettabyte equals 2,000 exabytes. That's a big number. And that's exactly what we wanted to see from liquid clustering, which helps pruning data during data skipping. These are some of the testimonies about liquid clustering from our customers like Shell, ePIP Data, and Cisco. The feedback has a common theme. They all like the query performance improvements. Just to quote, liquid clustering improved our time series queries up to 10 times. And we have observed remarkable improvements in query performance compared to the traditional Z-order and so on. Also, they mentioned the ease of use, such as without worrying about the cardinality or file size, eliminating partitioning bottlenecks, and reducing data skews. It was very humbling to hear this great feedback because the feedback matched our goals, fast performance and ease of use at the same time. So if you haven't tried liquid clustering yet, please try out today and give us any feedback. So back to this code. Now with liquid clustering, we can waive our data intelligence 1 and replace partitioning and Z-ordering with a simpler yet more performant cluster by class. There you go. Okay, so finally we are left with one more thing to simplify, that being the continuous maintenance required on tables. To solve this, I want to introduce predictive optimization, which we announced as a GA feature just 2 days ago. But before we get into details, let's revisit why we started working on predictive optimization. As we have been discussing, tables can be optimized for better performance, but which optimization should I run on which table, and how often should I run these optimizations? And it becomes really hard when you have thousands of tables to manage. So we worked on predictive optimization. It has an intelligence engine that determines which optimization should be applied to which table and when. And these optimizations are applied automatically by Databricks, so you don't have to worry about running them manually. And some of the optimizations that we currently support are compaction, liquid clustering, and vacuum. And we have more coming soon, which we'll talk about in a bit. Now let's go over a very high-level architecture overview of predictive optimization. If you look at the slide, I'm a happy Databricks user. Let's assume that I have a managed table under Unity Catalog, and I enabled predictive optimization for this table. And I'm reading and writing to this table through Databricks Compute. Once I start interacting with the table, the Databricks Compute will start sending some useful telemetry to predictive optimization. And the telemetry gets fed into the intelligence engine. We'll talk more about this component later, but this is the core component that makes the hard decisions on what optimizations to run and so on. Once the intelligence engine makes the decision, it schedules jobs through the scheduler, and the jobs are executed by serverless jobs in Databricks automatically to the table. So this is a high-level architecture overview of how predictive optimization works behind the scene. And now, let's take a bit closer look at the intelligence engine. Let's start with an example of how liquid clustering is run by predictive optimization. The first thing that intelligence engine needs to figure out is which table liquid clustering should be run on. To achieve this, the engine receives telemetry such as table usage, the current clustering quality for a table, and how much data is clustered versus not clustered, and more. Based on this telemetry, the engine runs to predict query speed, in other words, how much data will be pruned, and clustering cost, which is how long would it take to cluster the table, as if we ran clustering on each table. So it's a prediction. On top of that, using other signals such as table usage, the engine predicts expected return on investment, or ROI, for each table for clustering. Then it sorts by the expected ROI and picks tables that meet the minimum threshold for ROI. So in this example, table 2 has the highest expected ROI because its table usage is high, clustering cost is low, and query speed up after clustering would be high, which logically makes sense. We can do the same exercise for vacuum. For vacuum, the engine receives telemetry such as bytes added and removed, retention window, and so on. So this is a totally different set of telemetry from clustering. Based on this telemetry, the engine predicts expected ROI for running vacuum for each table. And it picks the tables to run vacuum. And in this example, table 1 had the highest ROI because the table had a lot of data to vacuum, but vacuuming cost was predicted to be low. So at the end of all of this, we have what optimizations to run on which tables. How about when to run? The intelligence engine looks at all the candidate operations, and based on their expected ROI and cluster utilization, it schedules job on the serverless such that cluster utilization is maximized, as shown in the graph on the right. For example, we start with clustering table 2, which has the highest ROI, and it is predicted to occupy all CPUs, so we don't launch any other jobs at the same time. But when we start vacuuming on table 1, we are expected to have idle CPUs, so we launch clustering on table 4 as soon as we see some idle CPUs in the cluster. So to summarize, the intelligence engine figures out what optimizations to run on which table and runs them in the most efficient way. And this all happens without you having to lift a finger. Now back to Sirui to talk more about predictive optimization.
All right, thanks, Jerry. So yeah, similar to Liquid with predictive optimization, we were really quite pleasantly surprised by the adoption during public preview, and that's what gave us the confidence to move it into GA as of this week. Within public preview, we saw over 1,500 customers turn predictive optimization on. As of when I last ran the query, we had over 5 exabytes under management in data that had predictive optimization turned on. And at peak, we saw days where we were optimizing over 2 petabytes of data. That's compaction, liquid clustering, and vacuum combined. And so we saw we were having a tremendous impact on customers, saving them millions of dollars in total per day. And don't just take my word for it. We've heard a lot of great feedback from a lot of customers. Just to showcase a few, we had Anchor tell us that when they turned this thing on, they were able to save 50% in their storage costs because we caught a bunch of tables that they forgot to vacuum, and also because of our compaction, they were able to see 2x improvements in query performance as well. So really excited about that. I remember being on a call with them and just seeing their storage costs fall off a cliff, and it was a fun moment for all of us. Second, similarly, a customer called Plenitude had a similar experience. Turned this thing on, 26%. Immediate savings, but they also saw continuous savings over time. But I think one of my favorite stories was with Toloka. This customer had built, as I'm sure many of you have, a custom maintenance pipeline to do a lot of the things that predictive optimization does. And so this pipeline was this bespoke thing that they had to maintain. It tried to do a lot of the similar things. List the tables, which tables should deserve to have which maintenance operations run. But after enabling predictive optimization and putting it through its paces, and we jumped on a call with them and walked through how things were working, it gave them enough confidence to actually throw away their existing DIY pipeline, no longer have to maintain it. And then on top of that, they saw that predictive optimization was able to further speed up their queries and make things cheaper as well. So really, really phenomenal stuff, we thought. And really a testament to the power of the capabilities, the intelligence that Terry talked about. Okay, so we're not done yet though, because even though predictive optimization we believe is super powerful today, our goal is to constantly be adding more and more capabilities to the product over time, so that your data just continuously gets faster and cheaper. One of the big things that we are taking a private preview as of this week is automatic statistics. This is one of the lines of code that we wrote earlier on. The challenge today is there are these statistics that you can gather for query optimization, for data skipping, but a lot of this requires you to either choose the columns on which to gather those statistics and or run a command to gather those statistics for you. And this raises a bunch of thorny questions around, well, which tables actually deserve to have statistics gathered on them, because it's not a free operation. And because of this, no wonder, when we look at our own usage, the usage of our customers, analyze statistics gathering is actually one of the least used optimizations. And so really thought there was an opportunity to make this just happen for you all where appropriate. And so that's what we do. So with predictive optimization coming soon, but currently in private preview, we are going to have the ability for it to collect statistics where appropriate for your workloads. So it's going to try and understand which workloads would benefit from those statistics. And then where appropriate, it's going to gather those statistics either at ingestion time, where it can be cheap to do so because you're anyways writing the data, or it'll do it as a backfill in the background with predictive optimization background jobs. And so overall, the effect is, in terms of benchmarking, what we saw is that your queries would just get even faster, right? Up to a third faster, 33% faster, because of the benefit of having these statistics. And so yeah, this is in private preview now. Contact your account team if you wanna give this a shot. Otherwise, look forward to this rolling out generally to wherever predictive optimization is available later this year. Okay, so with that, we wave the wand another time. Those lines of code go away. And so you're actually left with just a single line of code. Just the create table statement where you cluster by a particular field. So then the question is, are we done? Well, almost, but you still actually have to choose the clustering columns. And as Terry said, it's much easier to do that with liquid clustering, but we don't feel like our job here is yet done, right? We think there's one more thing we can do, which is what if we could decide the clustering columns for you? And so that's why we have, I think we announced in the keynote the other day, automatic liquid clustering key selection. So the idea here is, instead of you telling us what to cluster by, I mean, you still can, but instead of you could also opt into what we call cluster by auto. So you tell the data intelligence platform that at least for this table, you're comfortable letting us determine what the clustering column should be. And then what we will do is we'll make that determination for you, and then we'll keep the table clustered in that way. So how does this work? It's the same feedback loop we've been talking about, but applied to liquid clustering. So the first thing we do is we gather telemetry on your workloads. What are your tables currently clustered by, and what are the query patterns against those tables? And then from there, what we'll look at is, what is the universe of ways that we could alternatively cluster this table? And if we were to cluster the table that way, would we get enough improvements to justify the clustering cost? Right? So you look at all the queries that hit this table, you look at all the ways you could cluster the table, and if you mix and match those, are there opportunities there to actually cause better data skipping, which means less query times, which means less cost for your organization? And if we do figure out that there is opportunity for improvement, what we'll do is we'll go ahead and just issue the commands to recluster the table for you automatically. And by the way, we may not do it, right? If the table is never used, or maybe the table is already well clustered and it's already at an optimal state, we may just leave it alone, and that's perfectly fine as well. And so this is coming soon to private preview. We're super excited about it, and really we feel that it's the last leg in this journey of removing all of the code that you used to have to write. Right? So we're going to take this final line of code, wave our magic wand one last time, and now this table statement, the create table statement, is I think as simple as can be. And really what this means is it's much more amenable to self-service analytics, right? It's really democratizing data because not everyone could write the entire page worth of code that we started with, but we feel it's much easier to just issue a create table statement. Okay, the one last topic I have for you all is a question I get asked a lot, which is, well, it's all fine and good that I just have supposedly one line of code to write, but how do I actually know that you are doing a good job at replacing all the hard work and elbow grease that I used to have to apply? Right? And so that's why the final topic here is observability. We hear this question so much that we're investing really, really heavily into making sure that you have out-of-the-box observability into what we're doing, into all the waves of the magic wand that we're doing, and as also in just the overall data layout health of your environment. And so the first thing I want to talk about is something that's already available, which is when you enable predictive optimization, there is just a system table that comes out of the box. And this system table will give you full visibility into everything that we do. And that's true not only now, but for all the new optimizations that we're planning as well. And so, but even now, you can run this command right here, and it'll tell you, for example, on what tables is PO, predictive optimization, performing the most compactions. Or you can ask it how much total data is being vacuumed, or how much money it's costing you, or whether or not it's positive return on investment. And so on top of that, the second thing we're working on is, some people say, give me an even easier way to understand that information. So we're going to have a pre-built dashboard built on top of the system table, so you don't have to even put that together. And it's just a good way to visualize and share the impact that predictive optimization is having on your data. And the last but not least, something I think I'm the most excited about of these three is we're looking forward to a system table that tells you about your tables. And so the idea here is, out of the box, a table which each row is the state of a delta table at a given point in time in your environment. And so it'll have things like the size of your tables, the data layout health, like are there good statistics on it? Is it well clustered? Are the file sizes good? And so the idea here is you can just use this table to really easily understand, first of all, what are my largest tables? What are my most unused tables, et cetera? But then also to validate that we're doing a good job optimizing the tables that really matter to you. And so at the end of the day, our goal is that you can trust but verify everything that we're doing instead of just taking it at face value. And so we've seen that basically you can, because of the data intelligence engine, was a ton of code simplified to a single line. And we saw that the data intelligence engine is making your workloads easy, hands-off, but highly observable. We saw it was making your workloads fast, highly performant, thanks to things like liquid clustering and predictive optimization. And we saw that on top of that, we're making things efficient, right? We're trying to save you money by doing garbage collection, by vacuuming, things like that. And so at the end of the day, instead of playing whack-a-mole here, you can instead dedicate your time to providing business value, or just maybe take a nap. And with that, that is our talk. Thank you so much, everybody.